Hello, this is Dr. Liu, and in this video I will demonstrate some applications of Kepler's third law. As we have been introduced, Kepler's third law has two alternative formats. One of them is the period squared of one planet over the period squared of another planet is equal to the distance cubed of this planet to the Sun over the distance cubed of the other planet to the Sun. So this links two planets together, although we may not be necessarily interested in such relations, as say we're interested in only one planet at a time. So the alternative is this: t squared of that planet, period squared, is 4 pi squared over gm, then distance cubed. So this is true for a planet orbiting the Sun, and it should also be applicable if you're orbiting a planet as a moon or a satellite, man-made satellite. So let's see, for satellite, all we need to change is, for a satellite, it feels the gravity of the Sun, but compared to the local gravity of the planet, it's much smaller. So it's just a planet that binds the satellite to itself. So for satellites orbiting a planet, then m is mass of a planet. And the t is the satellite's orbit, or the orbital period. Satellite's period. And this r is distance. From the center of planet, from the center of the planet to the satellite. So this works the same way between a planet and the Sun, or a planet and its own star. So what can we use this for? Well, say for example, if you just search, say, mass of any planet in our solar system, we'll have some answers. I remember I was showing a table of different parameters for different planets. Okay, so here's the table again. As we see, there are all different planets here, and somehow we know their masses. So how do we know their masses? And also we know their diameters in kilometers. We even know their densities. This is assuming the planet somehow is a uniform density of sphere. And we know gravity. Gravity means the little g on the surface of a planet. How do we know that? Did we actually land any crafts on all of these planets and or satellites, such as the moon? And the rotation period, I bet we can observe that, right, through a telescope. And all the other things, orbital period, we can observe that just watching it, right? So some of these quantities that cannot be observed directly, such as mass and diameter. So how do we even get these quantities? So that would rely on the application of Kepler's third law. So let's take a second look at this format. This is a very important format here. So what this tells us is, if we were to orbit a planet, we certainly can and have sent out probes to various planets, right? And the most, obviously recent times to Mars. And say we just assume that our satellite, a little probe, is orbiting Mars. So what can we learn from that? Well, here's an orbital period. This is something that the satellite or a Mars probe. Let's just call it a Mars probe. The Mars probe can find out just by looking into the sky for repeating patterns of the stars in the sky. So it is able to count its own period, how long it takes to orbit that planet. So this is something that that can be measured by the Mars probe, and that is not really convenient to measure because how do you measure your distance to the center of a planet? Well, you can certainly measure your distance to the surface of a planet if you had some sort of laser to range your distance. Just send the lasers towards the planet's surface and let it scatter back, and just time to time, the time of flight, assuming that the laser's speed is near the speed of light, then you should be able to calculate your speed, not your speed, your distance to the surface of the planet, not the center. So we have something that is related to this. And what about the mass? Well, we definitely cannot weigh a planet, right? So let's play out a few scenarios and see how we can figure things out just by flying a probe around that planet. Okay, so let's see if we can measure period and also a d. This is distance to planet surface. This doesn't really get us anything because d is not r, right? If we have t and then if we had r, we would be able to solve for m, right? So here's what we can find. M is equal to 4 pi squared over gt squared r cubed. So if we already know the period and somehow we know the distance to that planet's center, then we'll find the mass of the planet, which is one of the parameters I showed you in that big table of different things of planets. So one way to do it is to say orbit high. I'm just imagining this. I'm not an astronomer or astrophysicist. So if you orbit the planet high, which means you're very far from the planet, so that your distance to the planet's surface is approximately equal to your distance to the planet's center. So something like this, I'll just draw. This is our satellite. This is a probe. I don't know, something's happening in the background. It makes drawing slow down. Okay, so here's the planet. Okay, so that distance is d, and the center to center distance is r. As we can see, if we orbit far enough, d and r are about the same. So we can certainly orbit the planet very far from the planet, and we'll be able to have an approximate mass. And we can also try this to say alternatives to several different orbital height. So orbit at several heights. So there will be something like a d1, distance to the surface, d2, and d3, and so on. So what this can be used for is, we know that this r is equal to r of the planet plus the distance that the probe is to the surface, right? So if we write it this way, then t squared, let's just use m. M is equal to 4 pi squared over g t squared, and then r can be replaced by r planet plus d cubed. Okay, so what we can do here is we'll have a number of different d's. We'll have a number of different periods to go with that, and that will give us a plot, basically a plot of the d and the t's. So let's actually use the original form, say t squared. So let's put them in parentheses. To the rest, gm r planet plus d cubed. So now what this is telling us is the t squared is a function of the d, and if we have enough pairs of a d and a t values, which we could just have the probe orbit the planet at several different heights, then we can do a fit of this function, and what the fit of the function will provide us is radius of the planet and also its mass. So separately we can find our answers just by doing fits, this is actually useful. A satellite or a probe carrying a computer will be able to do this. And also what's important was I discussed this in a previous video, is you can find out the surface gravity using this. So we had universal gravitation at surface. This is important because if we wanted to land anything on the surface, we need to know the gravitational pull at near the surface, so we can navigate that landing, right? So Fg at the surface, and that is equal to F little g. So Fg at the surface, F is g, m. This big M is the planet, and over R, trying to say Earth, no, radius of the planet squared, because we're at the surface, so we're one radius away from the center of the planet, and mg of that planet. So when the mass is divided out, we have g planet equals g m of the planet over r planet squared. So we needed this mass, we needed the radius of the planet in order to figure out the surface gravity. And from this fitting, we can figure out both. If we just orbit at different heights, we can do a fit of the results. We'll figure out both. So then we'll be able to say so some value, and we can plan the landing on the surface if we know at least this parameter. So Kepler's laws are quite useful for not just tabulating values, but also exploring a planet that we never have landed anything on it before. Thank you.